Alright, time for some notes. Our new chapter is all about momentum. So this is a new idea, so I'm going to walk you through what it is, what it means, what's it used for, and why do we need to know it. So let's start with this. What is it? It's defined in a very specific way. It's defined as the mass times the velocity. So given a mass of some object moving at some velocity, if you multiply them together, that is the definition for momentum. Alright, if we look at how the equation looks, we use the symbol P for momentum, and then mass and velocity we know already. And the reason we use the letter P is because when Newton actually came up with his first laws, he wrote everything in terms of momentum, actually. And this P stands for progress. These are some useless facts that you don't need to know, but just letting you know if you're curious where the P comes from, because there's no P in the word momentum, and that's just silly. Alright, why do we use it? We use momentum to be able to describe motion for more than one object at once. What we've done before is we've had problems where we've figured out motion, forces, etc., but everything either moved collectively together, so we have two boxes like stuck together moving, or we had things attached by strings all moving. The point is the entire thing was moving at the same velocity or acceleration. Well, now what we're going to do is look at things that move at different velocities at the same time. So the big idea here is collisions. So when things collide, bounce apart, stick together, how do we describe its motion? And that's why we use momentum. Okay, so let's recap the big ideas, the big picture ideas of what we've done. Beginning of the year, we talked about how stuff moved. So we could describe position, time, velocity, acceleration. We could basically say where something is, when it got there, and how fast it was moving. Then we walked through why did it move in the first place. So we talked about forces. We learned what causes an acceleration. Why does something move at a constant velocity without a force? So objects in motion stay in motion, etc. We talked about the why. Well, now what we're going to do is we're going to talk about how stuff moves, again, but we're going to be able to describe more than one thing interacting at the same time. So if things bounce apart at different velocities, we can actually handle that and know what to do. So as a quick example, this doesn't have numbers yet. We'll have an example towards the end of the video, but this would be one example. We have an object moving at some velocity at another object, and the questions that we can answer are things like, if they stick together, how fast do they move as a whole? If they bounce apart, how fast does each of them move separately? Those are the basically those are the questions that we're going to answer. They'll get a little bit more complicated as we go, but here's the big idea. And now I want to relate momentum in something that you know already. So I'm going to talk about Newton's 3 laws. So the first one, we pretty much know this off the top of our head. An object in motion stays in motion, objects at rest stay at rest, unless there's some outside force. What we're really looking at is a simpler way to say stay in motion or stay at rest is an object that has a constant velocity. So objects with constant velocity will keep that unless there's another force involved. Alright, so if we look back at our equation. Alright, I'm back. I had to pause the video really quick. So we were talking about objects at rest and objects in motion. Really, an easier way to sum that up is something with a constant velocity, whether it's 0 or whether it's actually has a velocity. if we look at our new equation that we just learned for momentum, if we have a constant velocity, our mass doesn't change, so therefore our momentum is going to be also a constant. So another way to write this, Newton's first law, is an object with constant momentum will keep that momentum. So what it'll look like is this. The momentum of something will be constant. Unless, so if it's not constant, then that means we already know there was a force involved. If you're driving in your car and you slam on the brakes, your momentum is not going to stay constant because you are changing the velocity of the car. So somewhere there's a net force acting on that car, and the momentum is also changed. Okay, here's where you can see this algebraically. Here's Newton's second law, F equals ma. I'm going to rewrite this a little bit in terms of velocity and time. So I'm going to change acceleration to delta v over delta t. All I did was substitute in. I didn't change the equation at all. It's still the same thing. It's just got different letters in it. If we look at the very top portion, sorry. I don't know why I said portion. The top portion, that's m delta v. Well, our new equation has momentum. It's in terms of mass and velocity. So if we have m delta v, what we really have is a change in momentum. So our force is equal to a change in momentum divided by the time. And this is what we said before. If the momentum changes, there had to be a force. Well, it turns out the change in momentum over however long it took is exactly equal to the force. Right now, if you're an AP Physics 1 student, ignore the next few sentences when I talk about calculus. But AP Physics C, here's where the calculus comes in. We've got delta P over delta T, so we have some change in momentum, some change in time. Alright, the delta means an average. But if we take that average smaller and smaller and smaller into tiny increments, small enough for a derivative, this is what it would look like. So if we had an equation of momentum in terms of time, then if we took its derivative, we'd now have an equation for force. All right? We'll have more examples on how to use this in class, but for now, just know that it exists. There is some calculus involved with force, momentum, and time. Okay, now this is for everybody. This is Newton's third law. If there's ever a force at all, ever, then there has to be some equal and opposite force. If there's a force acting on A by B, there's a negative force acting on B by A. Well, what I'm going to do is I'm going to rewrite this law in terms of momentum, where we just said momentum over time is equal to the force. So, if we have some change in momentum for A, we have a change in momentum for B, and it's negative. So if I add them together and resolve it, let me go back. Okay, so what I did here is, man, I'm all over the place. Okay. Alright, so I took the equation above and I just rearranged it to where it equals 0. So, so if we've got our change of momentum of one object over time plus the change of momentum of the other object over time, and we added them together, they would cancel each other out to 0. Well, I'm going to get rid of the delta t because it's in all of the terms, and so really it's just the momentum of one of them plus the momentum of the other one. So the momentum of one, and if we had any number of particles interacting, then if we totaled up all of their momentum, or all of their change in momentum here, then it would be 0. So however much one of them changed, the other one changed in the opposite. Okay, so this is called the law of conservation of momentum. And here's what it looks like in the most simplest form. The momentum before something happens, like a collision, of every particle added all together will equal the total momentum of everything afterwards. So let's do a few examples using this equation now that we have an idea. We've got a car moving at some constant velocity, and those are the mass and velocity. What's the momentum? Well, all you have to do is multiply them together. So 10,000 times 10 will give you 10,000. And notice the units. There are no exact units for momentum. Like in forces, the standard unit is the Newton. For a mass, the standard unit is a kilogram. For a length, the standard unit is a meter. Well, for momentum, there is no one standard letter that we use for the unit. What we do use is this: kilogram meter per second. So that is the quote-unquote unit for momentum. All right, now let's do an example with the conservation of momentum. So we're gonna have to use this idea here. We've got a momentum of everything before should equal the momentum of everything after. And for our example, we're going to use a cannon, and it's going to have a cannonball loaded inside, and we're going to shoot it. Okay? If you've ever shot a rifle before, or a shotgun, or if you ever shot a gun before, then you know that there's always a kick. So as the bullet leaves the gun in the front, then the gun actually kicks back towards you. And I'm going to show you mathematically why that happens. So if we look at this cannon right here, before it shoots, the cannon and the cannonball are both at rest. So their initial velocities are 0. That means their initial momentums are 0 as well. Alright, let me redraw it real quick, and let's give some numbers here. So my question is, if I know the mass of both the cannonball and of the cannon, and I know how fast the cannonball leaves the cannon, I want to know how fast the cannon is going to go backwards. Because like we said before, the momentum has to be conserved, and if the cannonball goes forward, then that means it's going to have to push the cannon backwards. So the question is, how fast did the cannonball move backwards? This is why you feel a kick. When we solve this, we're going to get a negative velocity. Okay, so here's our basic equation. The momentum before equals the momentum after. So the momentum before, let me back up. The momentum before, everything is at rest, so there's no momentum. So let's add up all the momentums afterwards. So the momentum of the cannonball is going to be the mass of the cannonball times the velocity of that cannonball after it's shot. And then the other one is just going to be the mass of the ball. Oh no, excuse me, I had this backwards. So the mass of the cannon times the velocity of the cannon. So what I'm talking about is right here. That momentum plus the momentum of the ball afterwards, they have to total to 0. So we can use this to our advantage when we solve everything and plug in our numbers. So we know everything except the velocity of the cannon. And from this point right here, we only have one unknown. We can solve for that. So when we solve everything out, you're going to get negative 1.4. So if we had our cannon set up like this, and these were our numbers, and there was nothing holding the cannon back, so it wasn't propped up against anything, I didn't have like the brakes on the wheel or anything to keep it from rolling. If you shot this, then it would move backwards that fast. So it would move backwards at 1.4 meters per second. Alright, I hope this helped. I know that was a lot of information, So if that didn't click right away, go back and rewatch some of the explanations and examples. And when you're feeling confident and you know what you're doing, then we can try tackling the problems in class.